I'm going to have a go at explaining this graph now so that you've had a chance to watch this and see if you still want to ask more in the meet tomorrow, because no one else has requested help on it and I just thought this might help better than in the meet. I don't know, we'll have a go, shall we? So let's have a look at this graph and see if we can help you get your head around it a little bit. So the graph is showing the relationship between the wavelength, and that's shown here in micrometers on the x-axis, and the intensity. Now, intensity is the power you have, the number of watts, spread per unit of area. And that isn't a quantity you need to be able to define for GCSE physics, but I added that in just so that the y-axis doesn't scare you. Basically, the more intense, and normally that would be in watts per metre squared. Here there's arbitrary units, but the more intense something is, the more power there is over the same area. So in terms of energy, the more energy is being transferred every second over the same area. I hope that helped. So first of all, this graph is showing that relationship between intensity and therefore linked to energy and the wavelength. But what makes this graph more complicated to look at is the fact that it's showing you 4 different temperatures and those relationships for each of those. So it's also bringing in the idea of how temperature is affected with the wavelength and this intensity. So the temperatures that you've got are the 3000 Kelvin, which is this red line here, and then the 4000 Kelvin, 5000 Kelvin, and finally this blue line here is the 6000 Kelvin. So the first question that I asked you was to think about how intensity is related to temperature. So to do this, we're looking at the peak, how high the peak is on this y-axis here. So if we look at 3000 Kelvin first, the peak here is a very low intensity. As the temperature increases and increases and increases, as the temperature increases, the intensity is also increasing. And that's all you need to worry about at GCSE level, really, okay, is that as the temperature rises, the intensity is also increasing. So how does temperature relate to intensity? The other question I asked you was how the peak wavelength related to the temperature. So the peak wavelength, the point here, is showing the peak wavelength. As the temperature goes up, the peak wavelength has dropped down to here. As the temperature goes up, it's dropped down. As the temperature goes up, it's dropped down. So as the temperature increases, the peak wavelength decreases. As the temperature increases, the peak wavelength decreases. And you can't state any more about the pattern of that from that graph. However, that's why I went on and I plotted some other graphs. Let's take a look at those. So I then took those same results and I plotted extra graphs. The first one to look at this pattern between temperature and intensity. So as the temperature increases, it's temperature here on my x-axis and intensity on my y-axis. As the temperature increases, we saw that the peak intensity also increased. And we couldn't say any more from that first graph. However, when I plot the data in, I know there's only 4 points of data from our graph, but I don't know how smoothly I can draw this line in for you. Yeah. But there is definitely a relationship. There is a curve best line fit. That's a terrible best line fit. Please don't judge me on that. But when you actually do take it further and do further analysis, you can actually see this non-linear relationship quite clearly. And again, you don't need to know that for GCSE, but I think it's quite interesting to see that pattern and link it to other ideas, especially when we think about space and astronomy units. So the other graph, we'll have a quick look at 2. So plotted results, but I only had the 4 results, didn't I? And then I've used this graph from Google. It's the blue line that we're looking at here. Okay, so plotting the maximum wavelength, peak wavelength, with the temperature, we can further look at the relationship, and there's actually an inversely proportional relationship, because if you double the temperature, you find that you halve the peak wavelength. And again, that I was saying that as it's really interesting to look at the patterns more than this is going to be tested at GCSE. The first graph, the colour graph with the 4 temperatures, that's the one that you might get asked about in a GCSE question, and that's the one that we'll finish with because we looked at a specific GCSE question. So let's finish with that one. So the exam question worth 4 marks. So this is really the same graph, it's just in black and white, and now there's only 2 temperatures which aren't specified for us, just we're told the lower temperature and the higher temperature, but it's exactly the same as that first graph, right? It's wavelength, this time in nanometers on your x-axis, and intensity on the y-axis with no units attributed to it because you don't have to know at GCSE, it would be watts per metre squared. So this is the temperature curves, and it's asking why is the filament lamp appearing brighter and less red as its temperature increases. So it's asking you to link that idea to this data. So first of all, we need to see what the graph is telling us. And it's telling us that the intensity of the radiation increases with a higher temperature. Because we can see here the lower temperature on the y-axis gives us a lower intensity than the peak wavelength high temperature curve. The intensity is much higher for the higher temperature, just like we analysed in the first graph in the lesson. Now we also need to think about that peak temperature. So at higher temperatures, this higher intensity, and that's happening when the wavelength, the peak wavelength I should say there, okay, follows the other pattern we talked about. So the idea that the higher the temperature, the lower the peak wavelength. Both of those ideas can be brought into this answer. The other thing to notice, and the mark scheme will help you to look through this idea a bit more as well, I'm sure, but at lower temperatures, the intensity of the radiation that's emitted is lower, and the range of wavelengths emitted, if you look at the width of this peak compared with this peak, the range of emitted wavelengths is greater at a higher temperature as well. And that means that it's emitting a greater range of colours of light. So at low temperatures, with less of a range, you're going to find that you don't see as much brightness because you haven't got the intensity, and therefore you get a duller red colour. I don't know if that helps. I hope it's helping. Always you can let me know if you need a bit more, and we have got the meet tomorrow. Okay, I hope it helped.